Introduction of linear algebra. Linear algebra is a branch of mathematics fundamental to various fields, play a crucial role in architectural design by assisting in modeling, analyzing, and solving problems related to geometry, space, and structure. Through the application of linear algebra, architects can effectively address the complex spatial challenge, optimize structural integrity, and enhance the aesthetic appeal of their design. This introduction will cover the key concept of linear algebra, illustrating how these mathematical principles are integral to the innovative processes in architectural design. There are some methods that can be applied in architectural design, such as transformation matrices. Transformation matrices are utilized to perform geometric transformation on objects, including translation, rotation, scaling, and sharing. Optimization techniques are employed to optimize resources, such as minimizing material usage while maintaining structural integrity, which involve the solving system of linear inequalities. Additionally, eigenvalue and eigenvector that are used to analyze and simplify the effect of linear transformation, proving particularly useful in stability analysis and optimization by indicating whether a structure will be stable or prone to resonances. We choose to apply Sarus rule in our assignment, so here is a background of Sarus rule. Sarus rule is a mnemonic method for calculating the determinant of 3x3 matrix that owned by French mathematician named Pierre-Frédéric Sarus. He is educated and later a professor at École Polytechnique in Paris. Sarus played a significant role in advancing mathematical education during the 19th centuries. His rule, which implies the computation of determinants, remained a valuable educational tool for its simplicity and efficiency, reflecting his broader impact on the field during a period of significant mathematical advancement. The reason of why we choose to apply Sarus rule in the modeling phases of architectural design is because it is easy when dealing with 3D model. Transformation and rotation of objects are frequently represented using 3x3 matrices. Sarus rule can be used to quickly compute the determinant needed for this transformation, ensuring that the models are correctly scale, oriented, and positioned.
Application of linear algebra in the field of architecture. Linear algebra is integral to efficiently utilize space within architectural designs. By using a linear equation to divide space into rooms, matrices can represent the relationship between different room types. Matrix representation helps in organizing and rearranging spaces within a building to achieve optimal layout. The title of our case study is Production Optimization House Layout. Okay, now let's get started. Imagine you are an architect tasked with designing a house that must contain a specific total number of rooms. The house needs to include a combination of bedroom, bathrooms, and living rooms. The total number of rooms must meet a client specification while adhering to space constraints. Linear algebra can help determine the optimal number of each room type. Here's come the problem description. We, as architect, need to design a house with the following specification, where the first condition is the total number of rooms in the house must be equal to 10. The second condition is the house should have twice as many bedrooms as bathrooms. Lastly, the combined number of bedroom and living room should be 7. The case study gives us a situation where the concept of linear algebra can be used to solve the problem. So the purposes of the case study are to understand the importance of linear algebra in the architecture field, to form an augmented matrix based on the equation of the system linear equation, to find the determinant of the system linear equation by using Sarus rule, to solve problems with system linear equation from information that has been collected, and lastly, to determine the optimal number of each room type according to the client specification.
In terms of methodology, we will calculate the exact number of rooms required for the house layout by applying the Sarus rule. Thus, in step 1, we will let any variable represent the number of rooms In this case, the number X, Y, and Z represent the number of bedrooms, bathrooms, and living rooms respectively. Next, the linear equation is changed in accordance with the problem description. First, the total number of rooms in the house must be 10, so S plus Y plus Z equal to 10 is the linear equation for it. The second problem description is, which could be expressed as S equal to 2Y, states that the house should have twice as many bedrooms as bedroom. However, we can rewrite this in a linear equation as S minus 2Y plus 0Z equal to 0. And the third is that there should be a total of 7 living rooms and bedrooms. Therefore, the linear equation is S plus Z equal to 7, or alternatively, S plus 0Y plus Z equal to 7. Thus, we may convert that linear equation into a matrix where it is 1, 1, 1, 1, negative 2, 0, 1, 0, 1. Next, in step 3, we use the Saros rule to get determinant A, X, AY, and AZ. We copy the matrix and we write the first two columns on the right side of the matrix to get the following in order to calculate the determinant A. Specifically, S1 is multiplied by the value on the diagonals from top left to bottom right, and the product is then added together. Same as S1, we can get S2 by multiply the value on the diagonals from top right to bottom left. Subtracting S2 from S1 obtains the determinant of A, which is negative 2 minus negative 1 equal to negative 1. Next, to find AS, we will use the same method as determinant A, but the difference is that we will change the first column to 10, 0, 7. So for S1 we get negative 20, and for S2 we get negative 14, where we then subtract it and get negative 6. And then for AY, we change the second column to 10, 0, 7, and we can get S1 equal to 7 and S2 equal to 10. Subtract them and we get a negative 3. And for the last one, AZ, we change the third column to 10, 0, 7, and we can get S1 equal to negative 14 and S2 negative 13. Subtract them and we can get negative 1. In order to determine the number of rooms, the final step is to get the value of X, Y, and Z by dividing determinant AX, AY, and AZ by determinant A. For AX, we divided the determinant AX by determinant A, where we get negative 6 divided by negative 1 equal to 6, so the number of bedrooms is 6 rooms. Then we divided the determinant AY by determinant A, where we get negative 3 divided negative 1 equal to 3, so the number of bedrooms is 3 rooms. And the last one, we divided the determinant AZ by determinant A, where negative 1 divided negative 1 equal to 1, so the number of living rooms is 1 rooms only.
So, based on the methodology, we need to find the values of bedroom, that is X, bathroom, that is Y, and living room, that is Z. From the questions, the system with linear equation can be written in a matrix form or simply as AX equal to B. First, we need to find the determinants for metric A by using the Saros rule, because the size of metric A is 3 times 3. As a result, the determinant of A equals negative 1. Since determinant of A is not equal to 0, we can find the values of X, Y, and Z using Cramer's rule method. To apply the Cramer's rule, we need to find the determinant of AX, AY, and AZ. We can also use the Saros rule method because the matrix for each of them is 3 times 3. At the end, the determinant of AX is equal to negative 6, determinant of AY is equal to negative 3, and the determinant of AZ is equal to negative 1. We can simply get the value of X, Y, and Z by dividing each determinant of AX, AY, and AZ with the determinant of A. X is equal to 6, Y is equal to 3, and Z is equal to 1. As a result, the design of the house should include 6 bedrooms with a total of 3 bathrooms and 1 living room. So, it is proven that we can apply the Saros rule to get the determinants for matrices with size 3 times 3, and is also applicable to Cramer's rule to get the optimal number of each room type according to the client's specification.
In summary, Saros rule provides a quick and efficient method to find the determinant of a 3 times 3 matrix, leveraging the matrix structure and the specific property of 3 times 3 determinants to avoid more complex methods. In architectural design, the simplicity and efficiency makes Saros rule a valuable tool for architects and engineers who frequently encounter 3 times 3 matrix in various aspects of their work, allowing them to perform necessary calculations swiftly and accurately.